Shut up and sit down.
What up, everybody? Welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host as always, and welcome to the podcast. Now, on today's episode, I want to talk a little bit about series and parallel circuits. Now, I've got an upcoming mini webinar. Again, you know I do these 2-hour webinars, and I got one coming up towards the end of June on series and parallel circuits and Ohm's law and basically the basics of theory. This is important when you're taking exams, right? Is understanding theory because they're going to be on exams. Now, when we get out in the real world, out doing the work, as electricians, we're out making the money. We probably don't think about it as much. There's no time, I guess, that I can think about it that the electrician has sat down and really contemplated a series versus a parallel circuit. And you're going to run into both during a normal installation, whether it's a commercial building or it's something that you're doing in a residential application. Again, whether you're doing receptacles, for example, if you're looping through the receptacles, then you're basically doing a series circuit. If you run the branch circuit and you're actually doing pigtails and you're coming off of that pigtail to a receptacle, then theoretically here you're doing, whereas you come to a junction box and you have pigtails off to the receptacle, but then the circuit continues on to the next receptacle, then that is parallel application. Either way, it depends on your installation. You can have both parallel and series applications. Again, that can happen with luminaires as well. And if you have just one luminaire, then it's probably from a switch, the source through the switch up to the luminaire and then back. And that's probably that's a series. The actual load is in series with current flow. So there's many ways that you could have this in an installation. But when it comes to an exam, they ask an awful lot of questions in the theory portions, depending on what state you're in, on basic, series and parallels, and maybe even what's called combination series parallel circuits. So we're going to be doing a webinar on that because I do want people to understand that. Again, it seems to be stressful for people that prepare for an exam. So I want to make sure that you understand it. Now, you might have learned this back in your electrical theory class, but the thing about electrical theory class is that we forget things, especially if we don't use them. Doesn't mean you don't know it. Doesn't mean we can't jog a memory. Doesn't mean you're inadequate in any way. I forget things that I just don't work with all the time. So I have the luxury of, obviously with this channel and of course with my academy, that I teach so many students all over the country that I just get to always get refreshed with information. And I like to share it. Everybody knows that I like to share it. So for my fast track students, we'll have a special session on Wednesday night. Again, I'll remind you, I should do this plug. If you want to learn the National Electrical Code, the Fast Tracks program is the easiest way to do it. It's 100% online. You interact with me. You download our app. You can send me questions at any time through the app. If you're working on a unit and you have a question, you can interact with me, which is kind of unique in this online education world that we live in, and the ability to interact. I mean, I'm not just selling you a book or DVD or something like that, and then that's it. It's all interactive. So you're going to learn. And one thing that I didn't have growing up is if I had a question, I had to go to certain people. I didn't know who to go to. And so that's one of the things I'm most proudest of with Electrical Code Academy. As we've built this through the years here, we've taken it to a whole new level. Okay. Everybody's a great educator. There's, code is code. Theory is theory. Everybody has a different style of delivery. Like me, hate me, whatever. My style is my style. And I've helped thousands of people. And others have helped thousands of people. And it's all good. It's all wonderful for this industry because it means that we get better electricians. We get better educators. We get better apprentices. We get journeymen who become masters. And now they get to share their craft with others. And it's a beautiful thing. Like I said, the electrical brotherhood covers many areas, whether you're licensed, you're apprentice, you're learning the trade, whether you're a union or non-union, it doesn't matter. We have one thing in common. We all love electricity. That is just a beautiful thing. So I like to share what I can. And of course, as a business, obviously people, some like it and some don't. You have to monetize that because, again, it is what I do for a living. Okay. So at the end of the day, it's the same as I'm not going to take money out of your pocket for what you do for a living. So let's talk a little bit about it. So when it comes to understanding series and parallel circuits, or a combination of series and parallel circuits, there's some pretty basic concepts that we want to keep in mind. And of course, I'm not going to get too detailed in examples tonight because, to be honest with you, unless I gave you a visual, unless you could see the circuit and see where I applied the resistance and talk about what the voltage drop across resistance at certain points in the circuit, it's going to be hard. So I encourage you to think about our webinar that's going to come up and sign up for it. As always, my webinars I keep them affordable. It's $25 as always for my 2-hour short webinars. And I'd usually stay longer than 2 hours, but I pack as much as I can in 2 hours. But also, if you're a member of the Fast Tracks, you can get our access to our Wednesday night live sessions that you can ask me a plethora of questions on the program or other electrical pressing questions you may have, and I try to answer them for you, which, again, is worth the price of admission only. We have some great Wednesday night sessions, but you can only get it if you're a Fast Tracks member or you're a VIP or general subscriber over on our YouTube channel. Now, YouTube is youtube.com/master the NEC. If you're interested in that, $9.99 a month for the general or $14.99 a month for the VIP, and you get some extra perks for VIP. All right, enough of that. So tonight's show is sponsored by Electrician Pride. Hopefully you'll check out Electrician Pride for all of your specific trade items. Okay, we don't get into the goofy stuff. All of our stuff is professional. You could put it on your vehicle. You could wear it on your shirt if you interact with customers. It's designed to tell everybody what you do and you're proud of your trade. So I'm going to run that commercial. God, I always got to have that commercial, even though I'm 7 minutes into this thing. I run the commercial, and then we'll get into tonight's topic. Today's show is sponsored by electricianpride.com, your one-stop shop for electrician-specific T-shirts, hoodies, phone cases, mugs, die-cut stickers, leggings, and so much more. Featuring unique designs for electricians, journeymen, and master electricians, as well as electrical engineers and electrical inspectors. For more information on all the products that are available, visit us at www.electricianpride.com today. All right, so for you that complain, I'm almost 8 minutes in, and now we're getting into the lesson. It is what it is. Sorry. Okay. All right, so the first thing we'll talk about is series circuits. And we'll talk about them from an exam perspective, but there's certain things that you have to remember that are kind of what we would say rule of thumbs, things that if you can remember these things, it makes it so much easier as you go in to try to do a calculation on a series or a parallel circuit. And it becomes critical when you're doing a combination, because in a combination, that's when you have both series and parallel in your example. And you're always going to start with the parallel, and you're going to try to work it down till it's a simple series circuit, because again, series circuits are much easier to calculate. So you're always trying to convert it down to the lowest denominator, if you will. So let's talk about some givens, things that you need to remember about series circuits. In a series circuit, current flows from the voltage source, whatever that might be. In a lot of our examples, it would be 120 volts. But again, you could get an exam where it's talking lower voltages. It might be a DC circuit, and it might give you 10 volts DC or 20 volts DC. It might give you this value, and it's got to give you a voltage. Now, there's ways that we can calculate voltage from a given example. And we'll cover that in our webinar as well as in our Wednesday night sessions. But there are certain things that are givens. And you have to remember that in a series circuit, when the current flows from the voltage source, okay, and it flows through every part of the electrical device that we're talking about, okay, in a single path, means it's just kind of in a circular path. You know, we talk about electrical circuits, and it has to be continuous, right? It can't be broken. That's when you put a switch in there and you break the circuit, and that's what turns the light off, right? You close it, turns it on. So it's a continuous. So electricity flows when it is a continuous path, okay, from the source. Now, in a series circuit, it's actually flowing from the source through the circuit, through all the electrical components, and then back to the source. That is a single path. All right. It's a single. Now, here's some things to remember about a series circuit, the properties of a series circuit. Very important, because these are things that we want to remember so that they actually flop into our mind, if you will, when we're working a series circuit. Number one, remember that resistance, which is going to be given to us as RT, resistance total, it's the total resistance of the circuit. Resistance is additive in a series. All right, so if I have 3 resistors in a series circuit, complete loop circuit, and I have 3 resistors that are 3 ohms of resistance each, then it's 3 plus 3 plus 3. So it's 9. So the total resistance would be 9 ohms. Okay, so think about that. It's additive when it's a series circuit. Another thing that's really critical to remember, and sometimes we lose sight of this, is that the current in amperes remains the same throughout the entire circuit. Okay, so current doesn't change in a series. Now, the voltage itself is additive. Let me give you an example. So I have one of those mag lights, right? And you put the batteries in it. And you're installing that. Those batteries go one on top of each other. They're being installed in series, okay? And the voltage is additive. For example, 2 1.5 volt batteries, you put them in series, it becomes 3 volt battery in a combination, right? So maybe that's what you need for the whatever you're putting the batteries in for. The current didn't change, but the voltage did. The current remained the same. So that's some characteristics to remember dealing with the series circuit. The current remains the same through the circuit, but the voltage is additive. All right. Now, the voltage source is what? It's the sum of all the voltage drops across each resistor. So in an example, like I said, if I had 3 resistors that are 3 ohms each, the voltage drop, okay, from whatever our starting voltage source is, the voltage drop across each one of those resistors is actually summation of that is going to add up to the same value as the source. So in our case, if we had 3 in the exact same resistors, it doesn't take us a whole lot to take the 120 and divide it by 3, and that is 40 amps. So that would be, 40 volts. I don't know why I said amps. 40 volts at each together, adding them up, the summation ends up being 120 volts. So that one's pretty easy. Kind of just give you an example so that you kind of see that the actual voltage itself is the summation across the voltage drop is actually the summation or the additive component of all of the actual voltage drop values from each resistor, and it's going to equal the source's value. Okay, so there's just something to remember in that scenario. All right, and there's obviously formulas that we can use to come up with this. And of course, if you haven't taken the opportunity to go over and read my blog on Ohm's Law, you might want to check that out. It's free. Just go over to the website, masterthenec.com. That's masterthenec.com. And you go over there and you'll see a little blog button at the top. Click on it and read my article in the graphics that I have up there on dealing with Ohm's Law. And it'll show you the formulas. It'll show you the full Ohm's Law wheel. But then it'll show you some shortcuts, some smaller versions, the PIE and EIR wheels that are smaller. Those are the ones that you can remember quickly on an exam, and you can just jot them down real quickly on your scratch paper to kind of, and again, you cover up the one you're trying to solve with your finger, and then it gives you the formula for the others. It's kind of a quick way to do it. And some people just remember this in their mind. But again, if you want to draw it really does help out. All right. So the next thing to remember with series circuits, these are kind of some givens, if you will, is that power is additive. So power being in watts, if we do the calculation, and once we calculate our watts at each resistive point, then you add them together and it becomes, again, additive. So the power consumption, let's say, and we'll use a formula for that, the power consumption at resistance 1 and resistance 2 and resistance 3 become additive and you add them together. So you still have to do the calculation to find what the power consumption is at that one resistor. And then you write that value down, and then you do the second one and you do the third one. But at the end, power is additive. So you add them all up, and that is your power consumption. Right? So those are some of the givens that we utilize. And again, the formula that we would use here, which is R for resistance, and the RT, small t, is the total resistance. So it's RT. And then it's equal to R1, which is the resistance of the first resistance source, resistor. And then R2 is the second one, and R3 is the third one. So in our case, RT equals, remember my example? That would be 3 ohms of resistance. 3 plus 3 ohms plus 3 ohms is obviously 9 ohms. So 9 ohms is the RT when it comes to a series. Now, that is so easy that's the reason why we want to take all combination, parallel, and series, more complex equations. We always want to try to work the parallels down so that we're working a simple series, because again, it just becomes so much easier to be able to do that calculation. And I think that if you focus on being able to break that down, then it makes it much easier to work the equations, right? All right, so that's just an example of that. And so I'm not going to get into any examples simply because I can't, it's hard to paint a mental picture, if you will, of it. So I'm just kind of talking about it and encourage you to, again, if you're studying for an exam, think about taking our webinar, or, if you're in the Fast Tracks program, make sure you attend the Wednesday night session or the recorded session of our Wednesday night that talks about series and parallels, because it's going to be beneficial to you. It might be the difference in 1 and 2 or 3 questions on an exam. In the real world, you're probably not going to use this that much. Obviously, you're not. But, you don't think about this. Ask yourself, when's the last time you ever gave this much thought when you're wiring a building or something? Probably never. But it is something that is going to be on exams for most part, if it's an electrical theory question. All right, so the next thing we want to talk about is parallel circuits. And what are some of the givens with parallel circuits? So in a parallel circuit, you got to remember that part of the current that's flowing through that circuit, same type of closed loop system, okay? But part of the current that's flowing from the voltage source is actually going to flow through each resistor that's being installed in parallel, okay? So whereas in a series, it's just kind of a loop. And in that loop, example would be just a typical branch circuit that you're running it out to a luminaire, from a switch up to a light. Maybe it's a bathroom light, and then you're coming back. Okay. The resistance of that lamp, okay, if it's an incandescent bulb, it's the lamp, and it's simply flowing through it. That is a series circuit, right? It's just simply flowing through it. It's in line with the circuit. Well, in the parallel, it's a little different, because the circuit will branch off, and then you have multiple legs that are installed in parallel, and, parallel being, each their own path, and then they come back together as they come back to the source. So the best example I can give to that is I'm running a branch circuit for receptacles, and I'm running it out, and instead of going directly to the device, I have splice pigtails in the junction box, and I jump from that over to the device, but then I keep on to the next receptacle, and so forth. So that's an example where the circuit's continuing on, but it's tapped, and it feeds a receptacle. That's being done in parallel. You with me? So if a load is there, the loads are going to be in parallel. And ultimately, they're going to end up coming back to the source, in that one branch circuit anyway. So, that's the best example I can give you. The other example I could give you is think of a complete circuit, and then when it goes out, there's a point where it splits off into 3 different legs, and it has a resistor in each leg. And then once it goes back to the resistor, at some point, it comes back together at the neutral, let's say, and then it makes its way back to the source. So it splits up into 3 different legs. That is parallel. Okay, that's a parallel circuit. So again, if you can't wrap your head around that, I apologize. It is a podcast, but definitely make sure you attend that webinar, and we'll go into some deep things like how to do voltage drop across resistors, how to calculate the total current, total resistance, power consumption. We'll even give you some scenarios about what if the current goes this way, that way. It should be pretty good. And for many of you, it might be just a refresher. And a refresher is always a good thing. Never a bad thing. All right, so let's talk about some givens for parallel circuits, which are different than series. It says in parallel circuits, part of the current again flows from the source, whether it's the 120 source for every day like we do, or it's an exam purely electronics type of example where it just gives you, 50 volts, 60 volts, 10 volts, whatever. It all works the same. Okay. Voltage is voltage when we're working these equations. All right. So again, it flows through every resistor in parallel. And the total current, now this is what's different. The current is actually the summation of the currents from each resistor. Now that's different, right? Because remember, in a series circuit, the current remains the same. In a parallel, the current is the summation, okay? The voltage is what stays the same, okay, as the voltage source, okay? Same voltage from the voltage source flows through each resistor equally, okay? So it's different than series. So if you got to remember this, and we'll talk about some givens here in a second, but if you just remember this, in a series circuit, the current remains the same and the voltage is additive. In a parallel, the voltage stays the same, but the current is additive. Just wrap your head around that. And if you can kind of remember those things or come up with some little snappy acronym that helps you to remember that, then you've got half the battle won in these calculations. It's just a matter of knowing the formulas, and you got your ohms wheels there. You ought to be able to really answer any question based on what you need. Now, you need two values to be able to solve a problem. So you need to have either the current in I, you need to have the voltage in E, you need to have the power in P or W, or W, watts. You need to have, or the EIR, R for resistance. You have to have two values to solve this. And in many cases, they'll give you enough information. They might only look like there's only one value there, but they give you the information to be able to solve for the second. And once you have the second, you can solve the problem. Okay. And we teach that in the webinar. So it kind of helps you. And again, it's purely for exam, because in the real world, I don't think people use it too much. At least I don't think so. I can tell you I've wired tons of houses, tons of high-end buildings, and I've never sat down and given series and parallel much thought. I really haven't. And you can say, well, Paul, you should have. Sorry, I'm being real with you. I never had to give it much thought. Okay. Anyway, so this is purely an exercise for preparing for an exam, or unless you just want to know these things. And a lot of students, apprentices, people are getting into it. They want to know how current divides, how these things work, and how, the difference between series and parallel applications. And they want to put it in the real world. Like, is there resistance in wire? Absolutely. And we'll discuss all that as well, but how you find that, how you look that up. And again, it can play a role in voltage drop. What's your voltage? But there's other formulas for that. But we're going to be focused on series and parallels. All right, some of the properties that we want to think about with a parallel circuit as opposed to a series circuit. Number one, again, the total resistance is less than any one resistor. There you go, right there, mind blown. So if I have, let's say that I have a 3 different resistors, and one is a certain value, say one is 6, one is 4, one is 3. The ultimate total resistance of those 3 in a parallel circuit is going to be less than 3, because that is the smallest resistor or resistance value in the equation when it comes to the parallel. It's always going to be less than 3. So if you're on an exam and your values are above 3, then you can discount those right away. Just forget them. You just increased your odds of getting that question right. And they will have it. They'll have one where they add them up and thinking you don't know this, and they'll put that one there. So that's 1. So you get rid of that. Now you've got a 33% chance of getting it if you guessed. Then you look at it, and you're probably going to see another one that's got a value that's just wonky, and it's not going to have any real factor. So now you have a 50-50 chance. And if you truly at that point understand how to do series and parallels, then you're going to nail that question. And again, we like to get the ones on exams that we know. We want to worry about the ones we don't know. We want to be able to answer the ones we do know. And so this is a simple way to attack those by understanding series and parallels. So the total resistance is always going to be less than any one resistor. All right. Next, I told you current is additive. Current is additive. Whereas in the series, current remains the same. Okay, so current is additive. Next, voltage remains the same through the circuit. So again, parallels, voltage remains the same. The current is additive. In a series, the voltage is additive and the current remains the same. If you just kind of lock that in, you've already won half the battle here. You just have to plug in the formulas at this point. The other thing I told you earlier, that in a parallel, voltage drop, that is the voltage value that drops across the resistive load, it says voltage drop is the same as the voltage source in all resistors. Okay, so across all these resistors, it's going to actually add up to what? The same as the voltage source, right? So again, voltage drop is the same as the voltage source in all resistors. Just remember that. And then, of course, lastly, it's the same for series. Once you resolve something down to find what the power, and then you want to kind of work towards the power consumption at each resistive point, power is additive. So ultimately, whatever your power value comes up, it is what it is. It's power, it's consumption. It's additive at each resistive load. Okay, so remember, power is additive. It doesn't matter whether that's series or parallel. Power is power, consumption's consumption. That is additive. But it's those other principles that you want to really remember to take with you as you do it. Okay. Now, there's so many different ways to do these calculations. There's a method to do where the total RT would be resistance 1 times resistance 2 over resistance 1 plus resistance. There's other methods to do this. When we're dealing with parallels, I like to use the formula RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So you always want to serve the lower portion of the equation first. So whatever the resistance value is in your equation, let's just say it's 10 ohms in the first resistor. Then when you're thinking the whole formula, and we'll cover this obviously in the webinar, but I want to always solve the value and work it down to a decimal. That's just how I like to do it. Again, there's 3 different ways that you can actually get total resistance. This is the easiest one for me to remember because it's the steps that make it easier for me to remember. And everybody knows I'm a decimal guy. I like to work things out to a decimal values. So in this case, the first one would be 1 divided by, in this case, if it was 10, 1 divided by 10, okay, and that would be 0.1. And then if the next resistance value in the parallel is 20 ohms, then it'd be 1 divided by 20, and that's going to be 0.05. And then if the third one was 30, it'd be 1 divided by 30. So there's 3 of them here. So that would be 0.03333. And when I start getting what's called sequential numbers like that, I do carry it out to about the 4th or 5th because it just increases the accuracy. Okay. Probably not going to need to carry all that out on an exam to get your answer based on the A, B, C, or D options that you have. But I like to do that anytime I have what's called repetitive number. That's just me. You don't have to. You can round up and do whatever and drop off. It doesn't really matter. But in this case, once you have all those values of the lower portion, then you just add them together. And once you add them together, then you come back to the equation where I take the 1 and I divide it into this new value that we worked out, decimal value. And when you do that, that's going to give you your total resistance. And I explain that, and we'll probably look at both forms, but that's the easiest one I find to remember. Because anytime you've got either 2 resistors or 3 or 4 or 5 or 6, you're going to end up using this formula. If you only have 2, then there's another formula you can use. You're going to choose any 2 of the resistors, do that formula, and then you can work it down, and you have to do it in pieces. If I do it this way, I can work the entire formula in one shot. And that's why that's the one I teach. But again, there are other ways to achieve this. You can even break it down and do Ohm's law as an alternative method. There's ways to do this by simply just breaking things down. You need to find the total resistance. Once you find that, then you're going to find the total current. And then once you do that, you just use typical Ohm's law to do it. So we'll probably talk about that method as well in my webinar, as well as our Wednesday night class. But I want to keep it simple. The formula that I'll probably be using is the RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So it's got about, 3 little steps in there that you've got to do, or 2 steps, but it's not complicated. And usually people can just memorize that. Right? So that's what I'll probably be going over. Anyway, that's the example. Now, if you're lucky enough to get an exam where you have a parallel circuit and all the resistors are the same, let's say I have 3 resistors again, and they're in parallel and it's 30, 30, and 30. Well, that's pretty simple. Since they're all the same, you take one of them and you divide it by the number of resistors that you have. In this case, 3 of them. So 30 divided by 3 is what? It's 10 ohms. Notice that I said that the value is always going to be less than any resistor. Well, 10 ohms is less than any of these 30s. So it's pretty simple. And if you're lucky enough to get a question where all of the resistance are the same, all of the ohms are the same, then it's a no-brainer. But you're not going to get that lucky. So we actually go through it and break it down. And by the time you're done with our webinar, you'll understand the basics of it. Of course, it can get very complicated. I do not venture into blowing your mind. We try to keep the basic fundamentals because, again, unless you're an electronics student and you're going into electronics, then you can get into the more complexity of it. Electricians need to know enough to get past the exam, and in the real world, they just don't utilize it. They just don't utilize it that much. So, but I do think it's important that you understand it. You understand the concepts of it. And then I will go into, for example, thinking about how to find the resistance of conductors. And you might have a load at the end, and somebody wants to know, well, how do I know what the voltage drop is at my load? And there's a voltage drop calculation that you can do, but I like to teach it how using this situation, because usually those 2 conductors are being run in parallel, and they're both resistance. Okay, so they both have a value, Chapter 9, Table 8, for uncoated copper or whatever you're using, and I like to teach that as well. But we're not going to go over that in this episode because, again, I'd have to try to my darndest to paint you a mental picture, and I don't know that I could do that justice on a podcast. So that's going to be it for tonight's episode. I do want to encourage you to look for that webinar. If you really are intrigued by this type of thing, I know sometimes people will not be. I get it. But if you really want to know and ask questions on series and parallels and kind of join me, I appreciate everybody that does. We have a webinar coming in June. Check our website out or our Facebook. We obviously will be posting about that. If you're not a member of the Sparky Hub, make sure you go to www.thesparkyhub.com and join. It's a great community. I think we'll have over 800 members now. Chime in, post your installation pictures, ask questions, just good brotherhood there, and hopefully you join us for that. But that's it. For you that are in the Fast Tracks program, studying for your license, or just trying to learn the NEC better, and make sure you attend this session when we have it on series and parallels. It'll be an awesome series. So till next time, folks, stay safe. God bless.
Shut up and sit down.